Problem 1 from the 2007 exam might be one of the easier problems that they've ever given, except for maybe the last part. We have a block of mass M is being pulled along a rough horizontal surface by a constant applied force of magnitude F1. I would immediately look at the problem and see if there's anything about constant forces or anything about a constant velocity. There's nothing about that in here, so I know that the block is going to be accelerating the whole time. In part A, it just asks us to put all of the forces on a free body diagram. So force of gravity down, normal force up, force 1 is being applied at an angle, force of friction is going to oppose it along the horizontal. Okay? Next part, derive an expression for the normal force exerted by the surface on the block. Since F1 is up, it has a y component in the positive direction, the force normal is going to be reduced. So the force normal is equal to Fg minus F1 sine theta. Bada bing, bada boom, done right there. Derive an expression for the coefficient of kinetic friction mu between the block and the surface. I know that the overall force on this object, the net force, is going to be equal to the mass times acceleration. And that's going to be the difference in the x component forces, F1 cosine theta trying to take us to the right, and the force of friction trying to take us to the left. So F1 cosine theta minus mu k multiplied by, I'm substituting in the normal force that we found in the previous part. Remember, they typically use information from the previous part in the next part. So don't just stop doing the problem if you got part A wrong. You would still get part B. You would get points here if you included the normal force here. A little bit of rearranging to find mu k, just kind of move things around, move this over, move ma to the right, and we get f times the cosine of theta minus m1 over fg minus f1 sine theta. Okay? Next two parts are like so simple, I think they might actually make you stop and think you're doing something wrong. They're just asking for the velocity as a function of time and the position as a function of time. There's a constant acceleration on this object, and that constant acceleration means that the velocity is going to be increasing at a steady rate, so it's going to be a straight line. Since there is an acceleration of the object, that must mean that there is going to be some kind of parabola here for the position as a function of time. So far the problem's been very, very straightforward. Dramatic pause. Okie dokie. Next part. Now they get a little crazy and they say if the applied force is large enough, the block will lose contact with the surface. So right there I start getting concerned about how complicated this is going to get. Derive an expression for the magnitude of the greatest acceleration, A max, that the blocks will have and still maintain contact with the ground. I'll be honest, I got real nervous on this part and I just started playing with it and I accidentally got the right answer. So I'm going to take you through my thought process on this. Okay? If the applied force is large enough, the block will lose contact with the surface. If we lose contact with the surface, then that means that the normal force is equal to 0. That means that the force of gravity down is going to be canceled out by the F1 sine theta. Okay? So then I kind of stopped here. Then I went down and I thought about the net force in the x direction. I said, okay, that would still be mass times acceleration. The net force is equal to ma. And now I only have F1 times the cosine theta because there's no friction. That's why the friction has gone to 0 there. So then I said, well, between these two equations, I should be able to figure out the acceleration. I rearranged this top one into F1 is equal to Fg over the sine theta. Remember that that Fg is also mg, so if you put mg, that's totally fine. I'm just using Fg for force of gravity. I substituted that down here, and now I've got ma is equal to Fg over the sine theta times the cosine theta. Replace Fg with mg so that the masses will cancel out. And then I've got cosine theta over sine theta, which is just the cotangent of theta. So the acceleration, if we have the normal force go to 0, the acceleration would be g multiplied by the cotangent of theta. Again, guys, I really didn't know where I was going on this problem. I just started playing with it, and if you check the solutions, this part's only worth 3 points. So there were 12 points of a very, very straightforward problem. Even if you didn't get these 3 points here, it's not really that big a deal. You're well on your way to a 5 on the AP exam. So don't let yourself get head faked on that. This problem was extremely straightforward. Pretty easy. We probably could have solved it in mid-September.